We're going to take a look at section 1.2, domain and range. So recall that the domain is the set of all inputs of a function and the range is the set of all outputs of a function. We use interval notation most of the time to describe domain and range of functions. So a reminder of interval notation: the lowest term is written first, the greatest term is written second, following a comma. Parentheses are used to signify an endpoint is not included, called exclusive, and brackets are used to indicate that an endpoint is included, called inclusive. And just a note, if the interval contains infinity or negative infinity, it is always not included or exclusive. So an example, if you have an inequality, x is greater than or equal to 2, what that looks like on the number line is a solid dot on 2 pointing to the right. Interval notation says, write your smallest value first in the interval, 2, a comma, the greatest value, since that's an arrow, infinity is the greatest value. Then take a look, x is greater than or equal to 2, so we use a bracket, inclusive. It goes to infinity, so we use a parenthesis, which does not include infinity. So there's, as an inequality, inequality is sometimes called set builder notation. So set builder notation is a method of specifying a set of elements that satisfy a certain condition that takes the form x and then a bar, statement about x, which is read as the set of all x such that the statement about x is true. So you would take this in inequality form, x is greater than or equal to 2, and in set builder notation, that would be the set of all x's such that x is greater than or equal to 2. So sometimes you're given intervals in interval notation and sometimes set builder notation. We just want to make sure that you can seamlessly go read the two. Okay, so another example, I've got set builder notation. The set of all x's such that 4 is less than x is less than or equal to 12. If you were to graph that on a number line, you would have an open circle at 4. You would have a closed circle at 12, and it would be all the values in between. So in interval notation, you would have a parenthesis because 4 is not included, 4, comma 12, and then you would end with a bracket because 12 is included. All right, so let's take a look at domain and range now that we know how to express domain and range. So if you've got a graph and you want to find the domain and range whose graph is shown, you take a look. The domain are all the x values. So the domain of the function, of this function, its function starts on the x-axis at -3 and it ends at an x value of 1. So the domain of this function, I'll use d, starts at -3. The open circle means it does not include -3. So we use a comma, -3, or a parenthesis. It ends at the x value 1, and then it includes the value 1 because that's a solid circle. So the domain of that function is from -3 to 1. The range are the y values or the outputs. The lowest value first. So the lowest value is -4 on the y-axis. It's a solid circle, so it includes 4. So we have bracket, -4, comma, and then the largest y value is 0. And there's an open circle here, but look, it actually touches 0. So that goes from -4 to 0. All right, you try the next one, pause, try the next one, and then when you're ready, come back and we'll work that one out. All right, domain are the x values. In this case, we start at -1, including -1, end at x equals 3. There's an open circle, so there's a parenthesis. So the domain is the set of all values from -1, including -1, to 3. The range, the lowest value is -5. It does not include -5 because we've got an open circle. And the highest value is 4 on the y-axis. It touches 4, so that's a bracket. So now that we've defined domain and range and how to express them in interval notation, we've taken a look at graphs. Now we want to take a look at some equations, and equations that you're familiar with, and how we find the domain, and in some cases also the range. So all linear equations, if you think about it, except for that are functions, and by the way, x, your vertical lines aren't functions, so all linear equations that are horizontal or slanted oblique lines, f of x equals mx plus b. The domain of all linear functions, you can put anything you want to in for x. It covers the entire x-axis. So the domain for all linear functions is from negative infinity to infinity. The range of all linear functions is also negative infinity to infinity, except if you have a horizontal line. The domain would be all real numbers, and the range would be only that value of your horizontal line. All right, quadratic equations, the domain. In this case, we want to take a look at the domain. The domain for quadratics, if you think about a parabola, this particular one has a negative. I'm not exactly sure where it is, but a sketch would open upside down. The domain, if you think about it, think about the values you can put in for x. For a quadratic, you can put anything you want to for x, and you'll get a value out for y. So the domain is all real numbers, and we express that, the open interval, from negative infinity to infinity. If you're asked for the range is limited depending on where the vertex is. So in this particular graph, you would have to find the vertex, and the range, whatever that value is, the range would be negative infinity to the y value of that vertex. Okay, so in this case, we're only asked for the domain. That's all real numbers. The range will depend on what your vertex is. If you have a function involving a square root, remember that we take square roots. We have looked at complex numbers, but we want to stay in the real number system here. So we can't take a square root of a negative real number and have it still be a real number. So when you're finding the domain of a square root function, take whatever is on the inside of that function, the 4x plus 13, and set it greater than or equal to 0. We can take the square root of 0 and any positive number. Then solve your inequality. Subtract 13 from both sides. We get 4x equals negative 13, and I should say greater than or equal to. Divide both sides by 4. We're dividing by a positive. We get x is greater than or equal to negative 13/4. So that's expressed as an inequality. To express that in interval notation, greater than or equal to, we start at negative 13/4 to infinity, open interval. All right, next type of function is a rational function or a fraction. So if we want the domain of this function m of x, negative 8x squared plus 4x all over negative 19 minus 2x in interval notation, the domain is everything except what makes the denominator 0. If you remember from the previous class, something divided by 0 is undefined. So what we do is we take the denominator, negative 19 minus 2x, and set it equal to 0. At what value of x does that equal 0? Add 19 to both sides. We get negative 2x is equal to 19. Divide by negative 2. X is equal to a negative 19/2. So the domain is all values of x except x cannot equal negative 19/2. So we can write that a few different ways. So if you wrote that in interval notation, it would be negative infinity to negative 19/2, not including 19/2, union negative 19/2 to infinity. So that expresses all the values in interval notation. If you want set builder notation, which is what we're asking for below, it's all the values x such that x, that's not what we want. Okay, so this question is done. The next question, we want to find the domain and then answer in set builder notation. Okay, so this is a different question right here. So if we want to find the domain of the function f of x equals x minus 9 over x squared plus 5x minus 36, we take the denominator x squared plus 5x minus 36 and set it equal to 0. And this will tell us what values of x we can't use. Factor, we get x. Two numbers whose product is negative 36, and at the same time the sum is 5. 4 times 9 is 36. In order for that to be a positive 5, that has to be a plus 9 and a minus 4. So we get x minus 4 equals 0, x plus 9 equals 0, x equals 4, and x equals negative 9. So x can equal all values except x can't equal 4 or negative 9 in the domain. So when you look through the solutions, let's see, the first one's close. That's positive 9, negative 4. Here we go. The third option, x can't equal negative 9 or positive 4. All right, next, and the last example is something called a piecewise function. So a piecewise function takes several different functions on different domains and graphs them all on the same graph. So in this case, what we have are 3 different functions. The first one, we have, I'll just use y. Y is equal to 1/2 x plus 5. Which is the graph of a straight line, but we only want to graph this line for x values less than or equal to negative 2. So you can do this a couple of different ways. You can graph it and then erase part of your graph from negative 2 and below, or you can plot a few points. I'm going to plot a point, this is less than or equal to negative 2, so I'm going to let x equal negative 2. And then I just need one other value less than that, maybe negative 4. I picked that because I have to multiply by a half. Then I get a y-coordinate. 1/2 times negative 2 plus 5. Negative 1 plus 5 is 4. So I'm going to graph the point negative 2, 4. And it includes it. If you put in a negative 4, you get 1/2 times negative 4 plus 5, which equals negative 2 plus 5, which is 3. So at negative 4, I get 3. Remember, you need 2 points to make a line. So I want to graph this line only for values less than or equal to negative 2. So there's my 2 integer points, there's my line. The next part of the piecewise function says, let y equal 4 between negative 2 and 2, not including negative 2, but including 2. So y equals 4 is a horizontal line through 4. I want an open circle at negative 2. So that open circle is going to go around the first graph I just graphed over to 2, and then I get a closed circle. The third equation says graph negative 2x plus 7 if x is greater than 2. I'm going to plot points again. Use 2 because that's our endpoint. We have an open circle. I just know I'm going to have an open circle on the graph. So I'm going to choose 2 and then a value larger than 2, which is 3. So I take negative 2 times 2 plus 7. Negative 4 plus 7 is 3. 2, 3. So there's 1, 2, 3. And I'm going to have a open circle. Put in 3, I get negative 2 times 3 plus 7. Negative 6 plus 7 is 1. 3, 1. So I'm going to graph this graph, negative 2x plus 7, for all x values greater than 2. So there's my piecewise function.